Okay, so we'll go ahead and get started with our last lesson of limits. All right, so today we're going to basically be talking about limits as they pertain to asymptotes. All right, so we'll talk about limits as x approaches infinity. All right, and we'll talk about asymptotes of a rational function. And we'll talk about the limit as x approaches a vertical asymptote as well. All right, so let's evaluate the limit as x approaches infinity of 1 over x using both a table and a graph. All right, so first we'll go ahead and do just with a table. All right, now typically when we do a limit, all right, we have to put whatever x is approaching, and we put that in the middle, right? Because typically we have to come at it from both sides, right? From the left and from the right, okay? Well, can we really do that with infinity? Can we come at infinity from both sides? No, right? Infinity is as far to one side as possible. All right, so common sense tells us that if we're trying to do a limit as x goes to infinity, that needs to be at the far right. Right. Obviously, if you were doing negative infinity, you would go to the far left. All right, so let's start with some numbers. Let's start really low with 1. If I plug 1 into x there, what do I get? 1, right? 1 over 1 is 1, bam. All right, what about if I plug 10 in for x? 1/10, which is 0.1. What about 100? 0.01, which is 1/100th. All right. What about, I don't know, 100,000? Probably 0.00001. I think. Tenths, hundreds, thousands, 10,000s, 100,000s. Yep, we're good. All right. So what about, I don't know, 100 million? All right, so we will have 0.000000001, I think. Looks good. All right. So obviously, as my numbers get larger, what does my overall f of x keep getting closer to? 0. All right. So the limit as x goes to infinity of 1 over x goes to 0, which obviously makes sense if you think about fractions. All right. The larger the denominator is, right, assuming that your numerator stays constant, the smaller the overall fraction is. Okay. All right, so now let's look at this graphically. All right, so if we go to y equals, all right, and we simply do 1 over x, we probably need to fix our window here. Whoops. All right, so obviously as x goes to infinity is going way, way out here. So it doesn't take very long, right, before we kind of see that it's just hugging the x-axis there, which means y is 0. Okay, and that's only to 10, right? We went out way farther than that very quickly. Okay, so with that in mind, let's try to talk about a couple of these. All right, we'll do a couple together. All right, and then we'll see if you guys can uh, figure out some of the others on your own. All right, so when we talk about infinity, right, actually, this is always kind of a little fun thing to do. So let's insert a blank page. Right. Do we all know the names of very large numbers? Have you ever been taught the names of very large numbers? Some people maybe, right? We all know basic numbers, right? We all know that's 100, right? Of course, we all know that's 1,000, right? We all know this is what? A million. We all know this is a billion. We all know this is a trillion. Who knows what this is? A quadrillion. Very good. This, quintillion. Yep. This, sextillion. Yep. This, septillion. Absolutely. Octillion. Yep, absolutely. Almost. Nintillion. A nintillion. What about this? Uh-huh. Dectillion. Yep, absolutely. What about this one? If you remember your polygons from geometry, it's kind of the same thing. 11 is like the little orphan Annie of numbers, right? Like, no, yeah, it's just called an 11tillion. Like, it has no special name. Like, it's not cool. Nobody cares for it. It's just, whatever. It's the same thing with polygons in geometry, right? You have the nonagon, you have the decagon, and you have an 11gon. Like, not very cool. All right. What about this? 12 gets a special name. It's cooler than 11. Almost. Dec is 10. But there's one thing that you add to it. Dodectillion. Yeah. A dodectillion. Yeah. And then after this, they're just all not cool. That's a 13tillion, 14tillion, so on and so forth. All right. Why don't you really ever use these numbers? Very true. There isn't anywhere near that much money in the world, right? It's not even close. But there are things where numbers get that large, right? So how do we typically refer to them? Oh, no, not so much. Kind of. I mean, that's the calculator's way of doing it. Scientific notation, right? Like when you talk about I don't know how many of you have taken chemistry, or when you start talking about molecules and moles and all of that kind of stuff, then you start just using scientific notation. Same thing with very small numbers, right? When you're talking about parts per million, or even way less than that when you're talking about solutions and stuff, right? You can definitely use incredibly just negative scientific notation with negative exponents that helps with very small numbers. So that's why we don't really do a lot with super large numbers, because there's not really a whole lot of practical application to actually, like, anytime you want to talk about some massive number, who wants to write all of this out, right? So that's why we typically just use scientific notation. All right. But also, when talking about very large numbers, when we talk about, as x goes to infinity, we need to think about just some really large number. Now, we can't really comprehend a lot of these numbers, right? It's like if you think about a octillion, it doesn't mean anything to you because you don't really have any experience or knowledge ever talking about anything with octillion, right? So somebody mentioned money earlier, right? Whenever I think of limits as x goes to infinity, I think of like super rich people, right? So now it's like Bezos, right? But before that, it was Bill Gates. And I used to have this little book that you put on like a coffee table or in the bathroom or something. And it was just all these random like little facts about Bill Gates. And some of them were like ridiculous. So whenever I think about like infinite money, I just think about if I had Bill Gates's money, right? He has like one of the little facts was if he were walking down the street and he dropped $100 bill, right? If he took the time to bend over and pick up the $100 bill, he would actually lose money because he makes so much money per second, right? That it wouldn't be worth his time to bend over and pick up $100 bill, right? Like you or I would be all about picking up that. I'd love to just follow that guy, dropping $100 bills. I wish that could be my job. Can I just walk behind you and pick up dropped $100 bills?
Like there was one where if you were to like constantly go shopping 24/7, he wouldn't run out of money.
Still couldn't spend it. Yeah, couldn't spend it. He if he went and bought a Lamborghini, right, it would be the equivalent, like as far as his percentage of wealth, like how much he would have to spend on a Lamborghini, it would be the equivalent of the average American going to a gas station and buying a 65-cent candy bar, right? Like you would think nothing about buying a 65-cent candy bar. He would think nothing about buying a Lamborghini, right? It's just irrelevant, right? It means nothing to his net wealth. Does anybody know what a McLaren F1 is? A McLaren F1. It used to be. I don't think it is anymore, but it used to be the fastest like street legal car that you could buy. Right? It's got a V12 engine. Yeah, it's got a V12 engine. The front seat is just one seat. It's like a cockpit of a jet. Like it's not, like you're in the middle of the car. It's called a McLaren F1. It's a British car, I believe. And but they used to have a plant in Texas, right? So they used to build McLaren F1s. So I don't think they have that plant there anymore, but they did back in the 90s. And Bill Gates wanted a McLaren F1. So, he called and he's like, I'm Bill Gates. I want a McLaren F1, but I want to be the one to drive it off of like the assembly line. Like I don't want anybody to have ever gotten behind the wheel of the car before. And they're like, you're Bill Gates. You can do whatever you want, right? So he takes his private helicopter to the plant. And this was back in the 90s. So think about today, right? It was $1 million car, right? Flat out $1 million. So he buys this $1 million car, drives it off the assembly line. And in Texas, if anybody's ever been to Texas, it's a lot of nothingness, right? There's just hundreds and hundreds of miles of flat nothingness for as far as the eye can see. So he just wanted to see how fast he could get this car going, right? So he's just hauling down the interstate. And eventually, he gets the attention of law enforcement. Of course, no cop car can catch a McLaren F1. So they're like setting up little roadblocks and they have a helicopter and stuff, whatever. He's Bill Gates. He's not some criminal. So he just pulls over eventually once he realizes that they're trying to get him to pull over. And of course, the cop recognizes him. It's like, oh, Mr. Gates. He's like, I'm really sorry, but, with as fast as you were going, that's reckless reckless endangerment. We have to confiscate the car. And he's like, here's the impound lot where you can go pick it up. And he's like, it's fine, keep it. And just left. So he bought $1 million car, drove it for like an hour. Police impounded it, and he just didn't even care. So like, that's how much money this guy has, right? Like, let's buy $1 million car just to have fun for an hour, right? So whenever I think of infinite money, I think of Bill Gates money, right? So whenever I think of limits as x goes to infinity, right, I think about Bill Gates's money. So thinking about that here with this very first problem, all right? Well, but it does help like visualize just super huge numbers and how much money, and even Bill Gates's money is nothing compared to infinity, right? So if you have $3, all right, or 3 pizzas. Let's say you got 3 pizzas, all right, and you're going to divide it by everybody in the world squared.
Wow.
How much pizza do you individually get?
Like a crumb?
Yeah, like probably a crumb that you wouldn't even be able to see. Yeah, like you wouldn't even be able to see it on your finger, right? Like you would need a microscope to see how much pizza you just got, right? So that is essentially what? Zero, right? Like you wouldn't be able to taste it, you wouldn't be able to smell it. You'd be like, I didn't get any pizza. This is unfair, right? So if you take 3 pizzas, divide it by everybody in the world squared, you get 0, essentially. So what is 4 minus 0? 4. So this limit would just be 4. Right? If you take 3 and divide it by infinity, nothing, right? You don't get anything. All right. So let's look at this next one over here to the right, just to the right of it. Look at this one here. All right. So now, if we're talking about Bill Gates' money, for example, all right, and he loses $3, is he going to notice? No, not at all. Now, in the denominator here, all right, well, now especially if you take Bill Gates' money and square it, right, multiply it by itself, and then you multiply that number by 5, and then you take 3 away, are you going to notice that 3? Are you going to notice? Absolutely not. So we don't care. That kind of just doesn't even factor into infinity, right? Similarly, if you had 2 times Bill Gates' money squared, right, and somebody came up to you and were like, here's $5. Like, is that going to affect your bank account in any way, shape, or form, right? No, it means absolutely nothing, right? Like, even if I just went up to Bill Gates and was like, Bill, I think you're a great guy. Here's $5. He's going to be like, you go ahead and keep this. You need it more than I do. Yeah, you need it more than I do.
I think that would have been.
Right. So, again, when you're talking about infinity, plus 5 means absolutely nothing. Okay. Now, of course, Bill Gates' money squared and Bill Gates' money squared, like, do matter, right? But if you have Bill Gates' money squared in the numerator and Bill Gates' money squared in the denominator, what happens to it? It just cancels out. So what's left? 5 over 2. Yeah.
This is confusing, but not.
This is like kind of confusing when you think about it.
Right.
Like,
I keep expecting it to get harder.
Right. It doesn't really. In fact, I'll give you some rules eventually that make it easier, right? Where you just kind of look at it and you're like, okay. All right. So looking at this one here, right, we have, of course, we have a negative up here, but does this plus 4 and plus 2 matter when we're talking about infinities? Bill Gates' money? No. Right. Adding 4 or adding 2 is irrelevant. Okay. Now, does this squared matter? Absolutely. Right. If you take Bill Gates' money and times it by Bill Gates' money, yeah, I want that kind of money. Right. So, yes, that does matter. Now, if you have Bill Gates' money up top, but Bill Gates' money squared on the bottom, right? Which one is way, way, way bigger? The bottom, right? And in fact, since infinity never ends, right? Infinity is always getting larger. And of course, infinity squared would be getting larger way faster than just infinity, right? So if you think about a fraction, a numerator and a denominator, right? If the denominator is getting super big, super fast, what does that mean to the overall number? It's getting smaller and smaller and smaller until eventually it just gets to almost what? 0, right? When you're talking about fractions, right? Like, think about if you have a million in the numerator, but you have a million squared in the denominator, right? Well, now you have a million divided by, I want to say that's like a quadrillion, right? So it's going to be like 0.00001, right? Which is almost 0, right? So whenever you have a higher power in the denominator, when you go to infinity, it's just going to go to 0. All right. So because we have a higher power in the denominator here, this whole thing is essentially 0. Okay. Now, what about, we'll look at this one here in the bottom right. All right. So again, this +3 and +1, probably not really going to matter a whole lot, right? All right. Now, we have an x cubed in the numerator and an x squared in the denominator. So is the numerator or the denominator getting bigger faster? The numerator. What happens to a fraction when the numerator is much larger? The number gets bigger and bigger and bigger. And if a number gets bigger forever, we say that that number is infinity. Yeah. So here, since the power in the numerator is greater, right, we say this is infinity. But if a limit is going to infinity, what do we say about that limit? It does not exist. Exactly. The limit does not exist. So this limit does not exist. Okay, so we actually, although I didn't specifically tell you, we've kind of gone through every kind of little scenario here that you could run into. So take just a few minutes and you can chat with your neighbor or anybody around you about what you think is going to happen to those other 1, 2, 3, 4 that we haven't done. All right. Also, congratulations to this class. I thought for sure, due to the sheer size of it, that you would be my first class that was quarantined, but you weren't.
Oh,
My fourth block is quarantined.
the whole month.
The whole class.
Well, yeah, how does that happen?
If you have 3 positive tests in one class.
What's the how
I'm supposed to be, but I'm fully vaccinated. So.
Oh, I was like, that's too bad.
Right. If I weren't vaccinated, I would have to be quarantined.
So then, what would happen to us if we were?
If what?
If you were quarantined?
There would be a sub here, and I would teach from home. But yeah, I thought just because there were so many people in this class that it would 100% be this class.
You never know.
Right? I also guess I could turn the lights on. He's like, I'm kind of nap. Yeah, it'll be nice to turn this one on. So. No, but that's the problem. We'll do the other one. Yeah. Yeah. All right. Our Are we ready to talk about them?
I guess.
I guess.
I'm a little bit just like, how do I actually understand this one and everybody else does? The one that everybody else understands and I don't.
It's a good question. Some people just get other concepts better than others. Okay.
I get this one, but I don't get that one.
So looking here, the limit as x goes to infinity of negative 6x cubed plus 1 over negative 2 plus x plus 3x cubed. All right. Does this plus 1 matter? No. Does this minus 2 matter? No. All right. Now, this is a slightly more interesting question. Does this plus x matter? Kind of, maybe. Some people are like yes, some people kind of. All right. Well, think about it this way. All right. If you have Bill Gates' money, I think he's 67. What's that?
What is it with Bill Gates?
Because he's super rich. He's the second richest man in the world, I believe. Jeff Bezos, the Amazon guy who owns Amazon. So if you have, some huge number, billions, trillions even, right? Think of the national debt, right? So if you have trillions of dollars and then you cube it. So a trillion times a trillion times a trillion. Yes, sir.
Bill Gates is actually the fourth.
Is he not? I've looked at plenty of different lists, and it fluctuates all the time. In fact, Bezos dropped below Bill Gates temporarily when he got divorced because he had to give up literally $80 billion to his wife and the family. And then one time Bill Gates got sued by the government, an antitrust lawsuit, and he had to just give half of his wealth to the government. So so that's kind of cheating too, right? Right. So of course, just in spite the government, he made all that money back the very next year. He's like, okay, I wasn't even trying to make money. Now I will. And but anyway, if you have a trillion times a trillion times a trillion, right? Now you're even way bigger than the number that we wrote down, right? We're way bigger than 13 tillions and all of that. So if you have a 13 tillion and you want to add a trillion to it, does it really do anything? No, right? It's kind of the same concept of, if somebody wanted to give Bill Gates $1,000, even if somebody wanted to give Bill Gates $1 million, it's not really going to affect his overall wealth, right? So no, believe it or not, the only term that matters is the highest exponent term. Right? It wouldn't even matter if it was an x squared, right? If there's also an x cubed or anything higher with it, it's not going to matter, right? So I understand, especially when you think about it in terms of money, billions of dollars matter. It is -2, absolutely, right? Because this doesn't matter. Whoops. This plus x doesn't matter, right? This x cubed and this x cubed just do what to each other? Cancel each other out. So -6 over 3 is indeed -2. All right. Using that same philosophy, what's this one? The 4 minus x squared? -1/5. That is absolutely correct. All right. Because obviously this 4 doesn't matter and this plus 2 doesn't matter. Right? So, and the x squareds cancel each other out. Of course, this negative up here is really -1, right? So if the x squareds cancel, you get -1 over 5, or -1/5. What about this next one here? Yeah, -2/3. Yeah, what about this last one here? We'll wait for Anna. Yeah, you're right. Yeah, it does not exist. All right.
It's either 0 does not exist or some random fraction.
And it does not exist because the top is getting larger faster than the bottom. Now, this is going to go to negative infinity instead of positive infinity, but it doesn't matter, right? One of our rules for limits not existing was that it increases or decreases without bound. That means it goes to positive or negative infinity. So negative infinity works the same way there. Okay. So I didn't. I just inserted that. All right. So a limit as x goes to infinity is simply just a horizontal asymptote. All right. You guys learned about asymptotes last year. All right. In fact, you guys probably learned these little rules for asymptotes, all right, which are actually all derived from what we just talked about with limits. All right. Specifically, limits as x goes to infinity. All right. So let's kind of go ahead and talk about this here. So limits, horizontal asymptotes, and the limits as x goes to infinity, they are the same thing. All right. So if the degree of the numerator is greater than the degree of the denominator, what happens if the top is larger? What do we say happens as far as limits are concerned? The limit does not exist, right? The limit does not exist. All right. Or in terms of horizontal asymptotes, there is no horizontal asymptote. All right, so that's our first case. Our next case if the degree of the denominator is greater than the degree of the numerator, what happens when the denominator is much larger? 0. Yeah. The limit is 0. All right. And the horizontal asymptote, which I call HAs, is y is equal to 0. So you kind of there's some slightly different terminology and way that you speak about it when you're talking about a limit as x goes to infinity versus a horizontal asymptote, right? They're the same thing in mathematically, but depending on what you're talking about, you kind of use different terminology, right? If the limit does not exist, that means that there is no horizontal asymptote. If the limit is equal to 0, that means that the horizontal asymptote is the line y equals 0. And then, of course, our last case, if the degree of the, I guess I should say, of the numerator and denominator are equal, then what happens? Yeah, and it's kind of hard to know how to state it when you haven't necessarily heard it before, but yeah, basically, all the other stuff doesn't really matter, and then we cancel out the x with the highest exponent, so we're just left with those leading coefficients, right? So the limit is the ratio of the leading coefficients. And as far as horizontal asymptotes are concerned, y is equal to that same ratio. Right. And we essentially can use those same rules for limits as x goes to infinity and for horizontal asymptotes. Fair enough? Okay. Okay. So now it wants us to graph f of x is equal to x minus 1 over x plus 3 on a graphing calculator and find the limit as x approaches negative 3 from the left and the limit as x approaches, and that should also be a negative 3 from the right. All right, so let's go ahead and pull this up here. So we had, what was it, x plus 1, x minus 1 over x plus 3. Is that what it was? Let's check. Oh, nope. I had that flipped around. X minus 1 over x plus 3. Is that what I did? Yep. Oh, yeah. Okay. I'm good. All right. Okay. So if we go ahead and graph this, it looks like this. All right. So obviously, what is happening here at x equals 3, the line x equals 3? They are approaching it. And what's that called? When a graph approaches a line but never gets to it? Yeah, vertical asymptote. Okay. So this is a vertical asymptote. All right. And you always get vertical asymptotes, all right, whenever the denominator is 0. Like whenever something makes the denominator 0, that's a big no-no in math, right? We're never allowed to have zeros in the denominators. All right. So whenever something does make the denominator 0, as far as its graphical representation, it will always put a vertical asymptote there. Okay. So as I approach negative 3 from the left, what is happening to my y? It increases forever, right? So I'm going to what? Infinity, right? Now, this is kind of the weird thing here. The limit as x approaches negative 3 from the left of f of x, all right? Typically, when a limit goes to infinity, there is no limit. We say it doesn't exist, all right? But when we talk about a one-sided limit, all right, it's okay to put positive or negative infinity because that actually is going to help us later on when we graph rational functions. It's going to let us know what that graph is doing as we approach a vertical asymptote, okay? And then the limit as x approaches negative 3 from the right. So as I approach negative 3 from the right side, what is my graph doing? Going down, right? Forever and ever, which is to negative infinity. All right, now, of course, what would we say about the overall limit there? Doesn't exist. Yeah. And it wouldn't even matter if they were both going to positive infinity or both going to negative infinity. It wouldn't matter. You still say the overall limit doesn't exist because it increases or decreases without bound. Fair enough. I know that's a little strange to think of it that way, but it actually helps us to determine whether it's going to positive infinity or negative infinity. Okay. Son of a biscuit. Okay. That is a fire drill.
Unless it's not a drill. Then I got the
Watch, we're gonna get outside.
Going down the
Like,
stairs, right?
Yeah, go all the way down the stairs to the right. Okay, so anyway, all right, these are all going to be one-sided limits as we approach a vertical asymptote, all right? Which means as we approach a vertical asymptote, we only have two options, right? We can either go up to positive infinity or down to negative infinity. All right, that's it. Those are the only two options. Would you shut that door for me? All right, so basically the easiest way to do this, all right, since we know we only have two options as we approach a vertical asymptote, all right, so here we have x approaches 4 from the left, all right? So what is a number really close to 4 just to the left of it? 3. Let's go even closer to 4.
3.9.
3.9. Love it. All right. So let's plug in 3.9. So if we do 3.9 plus 1 over 3.9 minus 4. All right. Now, we don't really care what the actual number is. Don't care at all. All we really care about is the sign, right? Because we know it either has to go to positive infinity or negative infinity, all right? So if it's a positive number, it's going to go to positive infinity. If it's a negative number, it's going to go to negative infinity, all right? So in the top, I have a positive number. In the denominator here, I have a negative number. A positive over a negative is negative. So this will go to, whoops, not -8, negative infinity. That's it. That's all there is to it. All right. And similarly down here, if we're doing the limit as x approaches 4 from the right side, what's a number very close to 4 just to the right of it? 4.1. So if I plug 4.1 into the numerator, I get a positive number. If I plug 4.1 into the denominator, I get a positive number. A positive over a positive is, of course, positive. So this will go to positive infinity. Fair enough. All right, take a couple of minutes to try to work out these last 4. It should be open. Jeez, is it? All right, so Let's take a look at these. These don't take too long. We do kind of have to be careful with negative numbers, though. So if we're looking here at the limit as x approaches -2 from the left, what is just to the left of -2? -2.1. All right, would be to the left of it. So if we plug -2.1 in for x, I get a negative up top. I get a negative in the bottom. A negative over a negative is a positive. So that would go to positive infinity. All right, so if -2.1 is to the left of -2, then -1.9 is to the right of -2. So if I plug -1.9 in for x here, I will get a negative in the numerator. I will get a positive in the denominator, which means this thing will go to negative infinity. All right, what is just to the left of 7? 6.9. So if I plug 6.9 in for x, I will get a negative in the numerator. I will get a negative in the denominator. A negative over a negative is a positive, of course. So this will go to positive infinity. And 7.1 would be just to the right of 7. So if we plug 7.1 in here, I will get a negative in the numerator, a positive in the denominator. So this will go to negative infinity. Any questions or concerns about one-sided limits as we approach a vertical asymptote? Nope. Sweet. All right, and that is it for the day. Of course, your homework is on Delta Math. And like I said, that's it for the unit. Tomorrow, you will have a practice quiz that you'll do in class. And then you'll have the rest of the class to work on your Delta Maths and stuff. And then Friday will be the quiz. Cool beans? Awesome.
Is the practice quiz for a grade?
It's going to count as, the practice quiz will count as extra credit.